Hello everybody. So today we're going to finish the last part of the Chapter 3, Section 3 notes on using or applying Newton's laws in everyday things. And today we're going to look at how we apply Newton's laws to circular motion. So we're going to revisit circular motion. And we did talk briefly about circular motion in Chapter 2 when we talked about all motion. Now, you already know that Newton's first law says that an object that moves at constant speed in a straight line wants to continue doing that because of its inertia, okay? So what if we don't want the object to move in a straight line, though? What if we want the object to move in a curve, like a circle? Well, in such a case, you need a net force to overcome the inertia. And that brings us to Newton's second law. Newton's second law says a net force will make a mass accelerate. In this case, the acceleration is not like the accelerations we've seen before. It is a change in velocity, but it's not the part of the velocity that we're used to having change. When an object moves in a straight line and accelerates, the value of the velocity, the numerical value, changes. Like on the interstate, if you're moving south on I-75 towards Naples and you're traveling at 55 miles an hour and you accelerate to 70 miles an hour, that's an acceleration because it's a change in the magnitude, the value of the velocity. But in the case of circular motion, it's not the value of the velocity that's changing, it's the direction. But because the direction is still a part of the velocity, it's considered a change in the velocity and therefore an acceleration. Okay? So, in this case, in order to travel in a circle, a net force must overcome your inertia and change the direction of your velocity. And yes, I've already got a little bit of this printed out. I'll tell you why. I was making the video earlier and I accidentally hit the stop button and I didn't want to print out a new one and start the entire thing over, so I just decided to go ahead and use what I had because it's not much, and then we'll continue from there. But you've got to have a net force to change the direction of your velocity. And anytime a net force changes the direction of your velocity so that you travel in a circle, we call that net force a centripetal force. Centripetal is a Latin word that means center pointing. So, centripetal forces always point towards the center of the circle. Now that does seem kind of strange, so let's talk about it a minute. On your paper, you have several pictures, so we're going to look at them one at a time. In this first one, you have a hand holding a string with a ball tied to one end, and it's being whirled by the person in a circle. Now, the velocity of the ball is always tangent to the circle. That means the line of the arrow shares only one point with the circle. So that means tangent. The inertia of the ball wants to follow that tangent at each point. It's trying to get the object to move in a straight line because that's what inertia wants you to do. Inertia wants objects to travel in a straight line at constant speed. Well, the constant speed part we have, but we want the direction to change. So we need a force to overcome the inertia and change the direction of the velocity, change the direction of the inertia. In this case, that force would be the tension in the string. So the tension in the string is acting as a centripetal force. It's making the object move in a circle. Because the direction of the inertia and the velocity are tangent, it changes from one point to another, staying tangent. Okay, if the string were to snap, whatever point the ball was located on the circle, it would follow that point, it would follow that tangent vector away from the circle. So if the string broke right here, the ball would fly this way. If the string broke right here, the ball would fly directly to the right. So wherever the centripetal force stops, there's no more force to change the direction, so the inertia takes over and makes it travel a straight line. So you must have a centripetal force to overcome the inertia and make the ball travel in a circle. Same idea here with the girl with the rope tied to the bucket. All right, the velocity at this point points back from the circle. I couldn't quite draw it back without you all not being able to see it, so I had to kind of draw it upward, but I'm trying to draw it back. In any case, the centripetal force right there points towards the center of the circle and is constantly changing the direction of the bucket's velocity as it goes around the circle. Not the magnitude part, not the numerical value, just the direction. Now here's a view from above, and it's a lot clearer to see. This is a car going around a circular track. Now, people don't stand in the center of the circle of a track with a rope tied to the car and make the car go in a circle. That tension doesn't work that way here, okay? You're not strong enough to do that. So if a car is traveling in a circle, what force is acting as a centripetal force to make the car's direction change? Well, it's friction between the tires and the road. The friction keeps the car from flying outward that direction. So it pulls inward to keep that from happening. Now, the direction of the velocity is tangent to the circle, and that's the direction of the inertia. So if the road were too slick, in other words, if there weren't enough static friction between the tires and the road, then it wouldn't stay moving in a circle. It would go sliding off the road along the tangent vector, okay? All right, that's why you don't want to go too fast along curves. If you're going too fast, the friction won't be large enough to keep you moving in a circle. Your car will slide on a tangent off the road. If any of you all have ever been along the off-ramps from the interstate where it's a clover leaf and you have to go around a circular path, they have maximum speeds posted. Usually they're about 20 miles an hour and you're supposed to slow down to that speed. So why is that? It's because if you're going too fast, the friction between the tires of your car and the road will not keep your velocity's direction changing. It won't overcome the car's inertia, and you will go sliding off the road and off the embankment, okay? So, now, look at this last picture. If you're on a roller coaster and you go around a circular loop, the centripetal force acting on each person and on the cars from the track points towards the center to change the direction of your velocity and your inertia. Your body and the car's body wants to travel a straight line all the time. So the centripetal force keeps it doing that. For the cars, the centripetal force is provided by the surface of the track itself, pushing down like this. For you inside the car, it's the seat under your butt, in this case, above your butt because you're upside down. That keeps you moving in a circle. All right, so now there's a word you need to know. Just be familiar with it, and that is centrifugal force. A lot of teachers on the middle school level sometimes use this term, and it's actually not a correct term. Centrifugal force is technically not a real force, depending on your frame of reference. Centrifugal means center fleeing. That means it points away from the center of the circle, but it's not what makes objects move in a circle at all. If we think about Newton's third law says, according to Newton's third law, and here's where we're going to pick up from where I made my boo-boo, all right, centrifugal force is the reaction force to centripetal force. Okay? Now, what do I mean by that? Well, let's look back up here. Okay? Look right here. The person's or the string is pulling inward on the ball. The reaction is the ball pulls outward on the string. That outward pull would be centrifugal force. But since it's acting from the ball and not on the ball being our object of focus, we don't consider it because we only look at the forces that act on the focus object, not the forces that act from the focus object. So since the reaction force, the centrifugal force, is a reaction, it acts from the ball, we don't care about that. We only care about the centripetal force that acts on the ball. Same thing with the bucket. And over here, same thing with the car. All right. The static friction pulls in, but the inertia of the car pulls out. Every action has an equal and opposite reaction. And the reaction to centripetal force is centrifugal force, and it acts from the object, so we don't care about it. Again, right here on the roller coaster, the track pushes in on the car pushes outward on the track. That would be the centrifugal force. And again, it acts on the track, which is not the focus object. The cars and the people are the focus objects. So we only care about the forces acting on them, not what they might do to other objects like the track. So centrifugal force could be considered a reaction force to centripetal force. But we do not consider it because it acts from the focus object and not on the focus object. Okay, when we look at the forces that affect an object, we look at the forces that are acting on the object, not the forces that act from the object on something else. Okay? All right. Now, we're going to revisit another term we looked at in Chapter 2, and that is momentum. We're going to revisit momentum and see how that relates to Newton's laws. All right, we defined momentum already. It is the product of an object's mass and velocity. Some people like to call it a quantity of motion. So momentum, which we said is a P, forget those little funky marks I've made above them. That's a habit I have from my other physics courses, and you all don't need to worry about that. But momentum is a lowercase p, all right? Remember that? Momentum. And here's mass, and the v is velocity, right? Okay. So it's the product or multiplication of an object's mass and velocity. And we learned that the more mass an object has, the more momentum it has. The more velocity it has, the more momentum it has. So this is a linear relationship. Either one of these gets bigger, the momentum gets bigger. Either one gets smaller, the momentum gets smaller. Now, here's our question. How does force relate to momentum? Okay? Well, we're going to start with Newton's second law. We already know that Newton's second law is F net equals the mass of the object times its acceleration, right? Okay. We also know that acceleration is a change in velocity. It's a change in velocity with respect to time. In fact, we could write that as final velocity minus initial velocity over time, couldn't we? All right, since this is how we define acceleration, let's stick it right there. If we do that, we get mass times final velocity minus initial velocity over t. All right, so all we did was substitute, which is perfectly okay. Now we're going to do a neat little trick called distribution. If you haven't heard it before, it's simple. The m is in the top, and it's multiplying this difference in the top. So what we can do is go in and say m times VF minus m times VI. There we go. We distributed the m through the top, and the t is still on the bottom. All right? So here's what we're going to do to get rid of the t. All right? We've got F net equals mVF minus m sub VI over t. Let's get rid of this denominator by multiplying it to the other side. We're dividing it here, so if we multiply both sides by t, the t will cancel on this side, and look at what we're left with. We're left with F net times t equals mVF minus mVI. But now wait a minute, we just said up here that mass times velocity is momentum. And look what we have, mass times final velocity, mass times initial velocity. So that means that this is the final momentum and this is the initial momentum, okay? So in fact, what we have right here is a change in momentum. Hang on, don't have enough room here. Okay, there we go, a change in momentum. All right, but if this is a change in momentum, what is this thing right here? The change in momentum is equal to the force that causes the momentum to change times the time period in which it acts. This product of force times time actually has a name. It's called impulse. Okay? Impulse. Impulse is the product of force and the time which changes, the force and time, that should be a comma there, which changes, and oops, there should be no D there, an object's momentum. And it's also equal to the change in momentum. So this force causes the velocity to change, which causes the momentum to change, and it's also, the force times the time, it's also equal to the change in momentum. Now think about this a minute. The bigger the force, the bigger the change in momentum. In other words, the harder you push, the more acceleration and therefore the more change in momentum you're going to get. The longer the time period the force acts in, the greater the change in momentum. In fact, guys, this is why they teach baseball players and golfers to swing through when they hit the ball. You don't just stop when the club or the bat connects with the ball. You swing through because you get a bigger change in momentum of the ball if that force acts over a longer period of time. So you swing through with your golf club or your baseball bat in order to increase the amount of time as much as possible in which the bat and the club are in contact with the ball. So the longer the net force acts, the greater the change in momentum will be there also. In fact, this formula has a name, although you don't need to know it. I'm going to tell you what it is anyway. They do refer to it a couple of times in your videos, and I think I even have a question about it. But this is called the impulse momentum theorem. Theorem. The impulse momentum theorem. It says that not only does impulse cause the velocity to change and therefore the momentum to change, it's also equal to that change, which is kind of cool because if you know one, you automatically know the other. If you know the change in momentum, you automatically know the impulse that was exerted. If you know the impulse, then you automatically know the change in momentum you're going to have, which is kind of cool. All right? Okay, now let's look and see how this can be applied. And I have another, oh, here it is. Your last page starts out like this, kind of cool. Look at that cute little picture I found. Okay, basically, the greater the force is, the greater the impulse and the change in momentum will be. All right? So look right here. If you have a truck moving with some momentum, M times V, if it hits a haystack, the haystack will exert a small force, but it'll do it over a larger period of time to stop the truck. All right? If the truck with the same momentum hits a wall, well, the wall will exert a large force over a small time period. The changes in momentum will be the same. Here, this is the initial momentum. Here's the initial momentum each time. It's the same momentum. And over here, the final momentum is 0 because the truck is stopped. It's lost all its momentum. So these two impulses are the same because they created the same change in momentum from mv to 0. mv to 0. Same change in momentum, so the impulses are the same. But which one would you rather be subject to? A small force exerted on you over a large time period to come to a stop, or a large force acting in a fraction of a second to come to a stop? Well, I'd want that one because, guys, it's the force that does you harm. So the smaller the force, the better off you are. And that's one of the things engineers try to minimize in a car crash. They try to minimize the force exerted to bring you to a stop. And they do that by trying to maximize the time it takes to stop by airbags and crumple zones. Okay? All right. In football, the defensive player applies a force for a given amount of time to stop the momentum of the offensive player with the ball. Now, if he can exert his force over a longer period of time, he's going to change the velocity of the other player more. But if he hits him and bounces off and doesn't actually hang on to him and keep applying his force, he's not going to change the receiver's momentum as much, is he? He's not going to stop him as easily. All right, now let's talk for a minute about what happens to momentum when objects collide. You've got to realize these are collisions that are taking place when one object interacts with another object. Okay, they collide. We say they collide. It's a collision. Well, when a collision takes place, we have to understand that momentum must follow a certain major rule of physics, and that is the law of conservation of momentum. The law of conservation of momentum. Momentum must obey this law. It's one of the most important laws in physics, okay? If no external forces act on a group of two or more objects, in other words, if the system is isolated, then their total momentum does not change. It's conserved. So if we look at the truck, it has momentum, but so does the haystack. It has 0 momentum. After collision, the total momentum of the system must be the same. So, where did the momentum of the truck go? Oh, it went to the haystack, because if you'll notice, the haystack has now been moved. Because it was moved, it had momentum. Right here, the truck crashes into the wall. Okay? It had momentum, now it does not. Where did that momentum go? It went into energy release, okay? It went into crumpling the truck up, and it went into just making a mess of everything, didn't it? Okay, so momentum has to be conserved. And here I have some examples of the types of collisions there are. For example, here's an object at rest. So the initial momentum is 0. Here an object's moving, so it has mv. Now then they collide. After collision, the final momentum of this ball is 0 because it's at rest. I should put rest right there so you all know later that's what that means. So what's the final momentum of this ball? It's the same as the initial momentum of the other ball. If this ball stopped, where did all its momentum go? It can't just vanish. It has to do something. It got transferred to the white ball. So now the white ball's momentum is the same as the orange ball's momentum before collision. So the total momentum, 0 plus mv, 0 plus mv, the total momentum is still the same before and after collision. Right here, we have an initial momentum of mv, and this ball, look which way it's going. It's going in the negative direction. So here we have an initial momentum of negative mv. All right? The two balls collide. Now look at the final momenta. Right here, the final momentum of this one is negative mv, and the final momentum of this one is positive mv. So what happened? Well, because they were going the same speed but opposite directions, and they have the same mass, and remember, these are identical balls. We need to make sure we understand that. That means they have the same mass. They're just different colors. All right? They bounced off each other. So in this case, the momentum is conserved because, look, we have mv plus negative mv. We have negative mv plus positive mv. It's the same two terms being added after as well as before. So the total momentum in each case is the same. All the balls did was bounce off each other. Now look at this one. All right, here are two balls going the same direction. So we have pi equals mv and pi equals 1/2 mv. See, it's only going half the speed, so it has only half the momentum. The two balls collide. Now, after collision, the final momentum of this ball is 1/2 mv, and the final momentum of this ball is mv. So what happened? Well, the orange ball gave half of its momentum during the collision to the white ball. So now the white ball has a whole mv, and the orange ball only has the half. But notice, 1 plus a half, 1.5 mv for the total. 1 plus a half is 1.5 mv for the total. So it's still the same total momentum before and after collision. The law of conservation of momentum must be conserved. All right, now look at this. What about the molecules colliding in this tank of gas? So here you have a tank of propane gas, and if we could see inside, we'd see all these little molecules bouncing around if we could actually see them on that level. And they're moving in all directions and bouncing around and colliding with each other and colliding with the tank. So as long as the tank stays closed, in other words, no outside influences like opening the tank. As long as the tank stays closed, the total momentum is constant. If you could add up every one of those little momenta, all right, say you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Suppose you have 15 particles, okay? So you have 15 momenta to add together. Whatever the total is, as long as the tank stays closed, it's going to stay 15 units of momentum, okay? Now, Does it change when two molecules collide? No, it doesn't, because all you do is you get a transfer of momentum from one to another, or back again. And therefore, all you're doing is moving the momentum among the particles. But since they're all part of the system, the total is always going to be the same. When one loses, the other gains, you still have the same total because it's all still within there, okay? However, if, someone opens the tank and gas escapes, then the total momentum does what? The total momentum changes. When an external force, like opening the tank so that the pressure difference from outside to inside pushes out some of those gas molecules, once you lose the gas molecules, you lose some of the momentum of the system. Like when you hook it up to your gas grill and you use it, you're going to lose some of the particles, so you're going to lose some of their momentum. So you've changed the total momentum of the system. But as long as the system stays isolated or closed from outside influences, the total momentum is constant, okay? Last thing, real quick, rocket propulsion. Newton's third law and the law of conservation of momentum also explains propulsion of rockets and jet engines. And I don't know where these lines came from because they're not on my original, but weird. In any case, whenever the jet engines burn the fuel is expelled out the bottom. And the force of the fuel being expelled out the bottom makes the rocket go up because of Newton's third law. For every action, there's an equal and opposite reaction, right? So when the fuel is expended outward, the action is the rocket or the jet engine goes the other way, all right? Even a squid uses a type of jet propulsion. Squid and octopi and cuttlefish, they actually use a type of jet propulsion too, only instead of burning fuel, what they do is they expel water. They take in water and expel it out forcefully, and that makes them go forward. So that is actually a type of propulsion. It's not jet propulsion like a rocket, but it's still propulsion, and it's kind of cool that it also pertains to these mollusks, the cuttlefish and the